Sample exam 3. Let S and T be independent events with the probability of S equal to the probability of T, and the probability of S union T is 1/2. What is the probability of S? Sample exam 3 of 8, problem number 1. We're given that the probability of S and the probability of T are the same. Let's call it X. And note that probability has to be between 0 and 1. We're also given that their union is 1/2. So, and they're independent. And so the union is the probability of S plus probability of T minus the probability of their intersection. So since they're independent, this is just the product of S times the probability of S times the probability of T. But let's put X in here to make it a little simpler. So we have 1/2, we have X, X, and then X times X. Well, this is a quadratic equation. We can solve it. So take everything to the other side. We end up with x squared minus 2x plus 1/2. Put that into the quadratic equation, solve it, and we come up with two solutions. Now if we take the positive piece of this, we end up with a value greater than 1. But x can only be between 0 and 1. So we have to take the lower value. So the probability of S is equal to this, which then can be changed to this to match one of the answers. Number 2, suppose X has a Poisson distribution with the standard deviation of 4. What is the conditional probability that X is exactly 1 given that X is greater than or equal to 1? Problem number 2. We're given that X is a Poisson with a standard deviation of 4. So now note that if X is Poisson, the expected value and the variance is equal to lambda. So the standard deviation is the square root of lambda, and they said that is equal to 4, so that implies that lambda is 16. And then we want to know the probability that X is equal to 1 given that we are greater than 1. Well, this can be written as the joint, so the probability that X is equal to 1 and X is greater than or equal to 1 divided by the probability that X is greater than or equal to 1. So this joint, both of those have to be true, and the only way for that to be true is that X is equal to 1, and we're changing this greater than or equal to sign to 1 minus X equals 0. And then since we know the Poisson distribution and the lambda parameter is 16, we can plug it in, which then simplifies to this, which then simplifies to this, which to match an answer. Number 3, a fair coin is to be tossed 3 times. The player receives $10 if all 3 tosses turn up heads, and pays $3 if there is 1 or no heads. No gain or loss is occurred otherwise. If Y is the gain of the player, what is the expected value of Y? So here we're given that we're flipping 3 coins. So if X is that outcome, it's a binomial with n equal 3 and probability 1/2. And so the outcomes of Y is we win $10 if X is equal to 3, meaning they all come up heads, so the probability of that is 1/8. We lose $3 if it comes up a 0 or 1, and the probability of that happening is 1/2. And we neither win nor lose if it's a 2, and the probability of that happening is 3/8. So the expected value is the possible values of Y times the probability of those Y's happening, which is this, which can be simplified to minus 1/4. Number 4, if X has a Poisson distribution and the probability that X is greater than or equal to 1 is 1/2, what is the variance of x. So problem number 4, we're given that x is a Poisson distribution and that the probability that x is greater than 1 is 1/2. So we change that to 1 minus the probability that x is equal to 0, and then we know that the distribution for a Poisson, where we don't know, what the value of lambda is, so we leave it just lambda. This simplifies to 1 minus e to the lambda. So then that's equal to 1/2. So take this piece to the other side, bring the half over, and we get lambda to the half. E to the lambda equals 1/2. Take the natural log of both sides. Now note that 2 can be brought up to 2 raised to the minus 1, which can be taken out, which then can be take the reciprocal. And so lambda is equal to 1 over natural log of 2. And since lambda is the variance of a Poisson, that's our answer. Number 5. An urn contains n white counters numbered 1 through n, n black counters numbered 1 through n, and n red counters numbered 1 through n. If 2 counters are to be drawn at random without replacement, what is the probability that both counters will be of the same color or bear the same number? Now, number 5 is an interesting problem, and we're going to try to solve it 2 different ways. So here we have, let's say, let capital C be both colors agree and capital N be both numbers agree. Now, since we're only drawing 2 pieces, the intersection of those events is the empty set. If we have 2 numbers agree, then the numbers can't agree. But if we have 2 numbers, 2 chips where the numbers agree, then the colors can't be the same. So the intersection is the null. And we're asked about the probability that both colors agree or both numbers agree. So that's equal to this probability. The probability that both colors agree plus the probability that both numbers agree. So we're going to introduce some notation here. We're going to let C1 be the color on the first draw and C2 be the color on the second draw. And similarly, and we're going to use that to find this. And then we're going to have N1 be the number on the first draw and N2 be the number on the second draw. And we want to find the probability that the color on the first draw is the same as the color on the second, summed over all possible colors that we could choose. Now the colors are white, black, and red. So we're summing 3 colors here. Here, for this probability, it's the probability that the first draw is in and the second draw is in, summed over all possible values. So this can be changed to a conditional. And I like that because we can find the probability of, drawing a specific color, and then once we know what color is drawn the first time, we can find the probability of drawing that same color the second time. So we have to sum over each color. So let's do white first. So the probability of drawing a white is 1/3. And now once we draw a white, what's the probability the second one is a white? Well, we used to have n whites, but now we have n minus 1. So there's n minus 1 over 3n minus 1. That's probably drawing a white. And then we do that for the same, for black, and we do that for red. And then for the colors, for the numbers, each number, it's going to be the same probability for each number. So there's going to be n times whatever this probability is. And the probability that we draw a specific number is 1 over n. And then the probability given that number n, what's probably the second time we draw that n, which there's only two numbers left out of the 3n minus 1 possibilities. So this is the probability. And we could have taken 3 times one of these, but illustrative purposes we didn't. Now this can be simplified to this plus that, which is that. Okay. So now the second way to do it is, if we think about the number of ways that capital C or capital N can happen, so that's the number of ways that we can have the same color or the same number over the total possible ways that we can draw to, is this. So the denominator is 3n choose 2, so that's the total number of ways. Now, to pick the probability to pick 2 colors of the same kind. So for instance, probability to pick 2 reds is n choose 3, but there's 3 colors, so it's 3 times that. And here, the number of ways that we can draw 2 numbers of the same kind. So for any specific number, so let's say number 1, there are 3 choose 2 ways to pick up, to pick 2 ones. So, because there's 3 ones from each color, and then we just need to pick 2 of those. So 3 choose 2 is 3 over the total number of ways to choose 2, 3n choose 2. But that was for a specific number, say 1. There's n ways to have different numbers, so it's n times that. And then that can be written as this, and then it simplifies to the same answer. Number 6. A random variable x has the density function shown below. What is the probability that x is greater than 1? So number 6, we're given this triangle, and it goes out to some number b, and the height is 0.2. So note that this line goes through the origin, so the form of that line is y equals kx. It's some slope, and it goes to b. So to note that the area of this triangle has to be 1. So we have 1 equal, and the area of a triangle is 1/2 the base times the height, and the height is 0.2, which is 2/10. So simplifies to b equals 10. Now there's different ways to find this slope, but rise over run is what slope is. So k, the slope of that, is rise over run, and the rise, it goes up 2/10 for every b distance, which we found to be 10. So k is 1/50. So now to be probability that x is greater than 1, which, pick a number 1 and then to be over here, is going to be the same as 1 minus the area of the triangle over here. And calculating areas of triangles are pretty straightforward. So we want 1 minus probably the x is less than or equal to 1, so that's another little triangle. So it's 1 minus 1/2 the base times the height. Now we're at 1, so if you put 1 into this equation, you get k, but k is 1/50th, so that's what that is. 1 minus 1/100, which is equal to 99/100. Number 7. 60% of new drivers have had driver education. During the first year, new drivers without driver's education have a probability of 0.08 of having an accident, but new drivers with driver's education have only a 0.05 probability of an accident. What is the probability a new driver has had driver education given that the driver has had no accidents the first year? So number 7, also an interesting problem. Here we're given a bunch of information, okay? And to make it easier, I'm going to let capital B be that new driver has an education, and capital A be that the new driver has an accident. We're given the probability of an education is 0.6. We're also given the probability that there's an accident given they have education is 0.05. The probability that there's an accident given there's no education is 0.08. So now from these three we can start building our knowledge. They either can have an education or not, so the probability of not having an education is 0.4. And then notice that given they have education, they can either have an accident or not. So this and this add to 1, so we can find that, which is 0.95. And the reason I'm doing it this way is because the answers, now the first time I solved this, I solved it and I didn't come up with one of the answers. Well, I did. The numbers exactly equaled, but the way that it was written was sort of tricky. They write it in terms of these probabilities, so I went ahead and found them. So that's 0.95, and the same way here. So given their no education, they can either have an accident or not have an accident, so those have to add to 1, so this is 0.92. So now here, we're going to need this piece in the equation in a second. So the probability that we do not have an accident is the probability we don't have an accident, intersection that we have education or not education. And this is the whole sample space. So this is 1. And so this is a smaller set than that. So the intersection is just this. But then we can break this up into a complement, or no education, intersection with an education, and no accident and no education. But then we can change those to conditionals. And then these numbers we found up here to be this. And I'm just going to leave it like that because that's the way the answer is. Well, the problem is asking that what's the probability that we have had education given that there was no accident? So that can be rewritten as the joint of no accident intersect education divided by the probability of no accident. Well, this top piece, no accident intersect E, is actually this piece here. And so we found that. Okay, so we can plug this piece in for the numerator. And then the denominator of probability no accident we found as the whole thing. And this is the answer that is given. Problem number 8. When 2 fair coins are tossed, what is the probability of getting no heads exactly 4 times in 5 tosses? So problem number 8, let's let Ti be, it could take on the values of 1 or 0. And it takes on the value of 1 if there's no heads in those 2 coins that are tossed. And it takes a 0 if there's at least 1 head. And so the probability of Ti is, meaning that it equals 1, is the probability that we don't have heads. That means we tossed a tail and a tail, so it's 1/4. So the probability that there's no heads is 1/4. Now T is a binomial 1 and 1/4, but we're interested in 5 tosses. So the sum of these TIs, which is binomial 5 and 1/4, because there's 5 trials. And then the problem asks, what's the probability that we have exactly 4? X is 4. So that means we have 4 of the 5 of these end up with no heads as their event. So that's just a binomial. 5 choose 4, 1/4 to the 4, 3/4 to the 1, and then that simplifies to 15 over 4 raised to the 5th. Number 9, 5 fair dice are thrown. What is the probability that a full house is thrown? That is, where 2 dice show up one number and the other 3 dice show up a second number. Now this one here is also a pretty tricky case. So we're given 5 dice or 5 die, and we want the probability that we roll a full house. So let's look at a specific event. So let's assume that 2 of the dice are the value A, and then the other 3 are value B. Okay, so I just called it die I and J, and it could be any of the 5 dice, but we're just picking 2. So each one of those have to equal a value of A. So those are independent. So that's 1/6 times 1/6. And over here, die K, L, and M, they also have to be a value not equal to A. And so the probability that those, since they're independent, it's 1/6, 1/6, 1/6. So the probability of this event happening is 1/6 to the 5th. Okay, but the number of ways that we could choose different A's, remember there's 6 possible values. It could be a 1, 2, 3, 4, 5, or 6. And then this has to not be that, but the possible values are 1, 2, 3, 4, 5, 6. So the number of ways to choose different A and B is actually permutation 6 to 2. So there's 30 different ways that we can choose values for A. And now, what's the number of ways that we can choose 2 die? So like if we choose 2 of them to equal A, then the other 3 are chosen, so they don't have an option. So the number of ways to choose 2 die, so say I and J, is 5 choose 2. So there's 10 possibilities. And this is also, you could think of it as what's the probability that we choose, the 3 die equal B. Well, 5 choose 3 is also 10. So once you choose either these 2, then those 3 are determined. Or if you randomly choose these 3, then those 2 are determined. But either way, there's 10 possibilities for this specific case. So the probability that we have a full house is combinations 5 choose 2 times permutation 6 choose 2 times the probability of any one of those events, which is this. So the probability is 10 times 30 times 1/6 raised to the 5th, which is can be written as 50 over 6 to the 4th.